Okay, here's section 10.2. And our learning targets are first we're going to determine whether events are independent events. Then we're going to be finding probabilities of dependent and independent events. And then we're going to be looking at some conditional probability. So the first thing I want to talk briefly about is independent events. What does it mean for an event to be independent? Well, that just really means that one event does not affect the occurrence of the other event. So what I like to think about with independent events is what we've kind of been looking at in last section. If I flip a coin and roll a dice, the roll on my dice does not have anything to do with my flip of the coin. So those two events are independent. So now let's look at our probability. So two events, A and B, are independent if and only if the probability that both events occur is the product of the probabilities of the events. So what we were really looking at is this is kind of what we were looking at in our last section. So I've got the probability of A and B happening, right? So two events is I look at the probability of the first one happening and I multiply that by the probability that the second one happens. Again, let's look at our coin flip and our rolling a dice. What if I want to find the probability that I flip a heads and roll a 6? I can look at the probability that I flip a heads and then I look at the probability that I roll a 6 and I multiply those together to find the probability of the whole thing happening. So that's some independent events. So let's look at this example. This is example number 1. So a student taking a quiz randomly guesses the answers to 4 true-false questions. Use a sample space to determine whether guessing question 1 correctly and guessing question 2 correctly are independent events. So the first thing I want to look at is looking at my sample space. So I have this example back on page 539, and this is where they just wrote out all of the possibilities. So if I look at that chart, I can see what I'm looking at. So let's go ahead and look at that chart. So here's what we were talking about. What we've done here is we've looked at all of the possible sample spaces. And remember that a sample space is all of my possible outcomes. So I could possibly, guess every question wrong. I could guess the first one right and the rest wrong. I could guess the first one wrong and the second one right, and continuing out. So here are all of my possibilities written out. So I want to look at that. So I want to look at the probability that I was correct on question 1. So I can look and count how many times in this sample space I was correct in problem 1. So here's 1, here's 1, here's 1, here's 1, right? And I can continue and just count the number of times I was correct in question 1, which was 8 out of my 16 possibilities. So then I can also look at, was I correct on question 2? Regardless of whether I was correct on question 1. So again, I go to my sample space and I count how many times was I correct on question number 2. So then I want to look at the probability that I was correct on both of those, on question 1 and question 2, which was 4 out of 16 or 1/4 of the time. So because I can actually take these and multiply them together, my events are independent. So what I did here to find these 3 probabilities to start with is I actually looked back at my sample space, which was written out here. Okay, so then I can look and say, well, could I multiply the 2 together to get my final answer? Yes. So since I can do that, my events are independent. And if we just think about it, that actually makes sense because it doesn't matter what you answer on the second one because they're different questions and they don't have to do with each other. So now let's look at example number 3. So a group of 4 students includes 1 boy and 3 girls. The teacher randomly selects one of the students to be the speaker and a different student to be the recorder. Use a sample space to determine whether randomly selecting a girl first and randomly selecting a girl second are independent events. So first I want to write out my sample space. Okay, so there's a possibility that I can have 1 girl. There's a possibility I can have 2 girls, right? Because there's 2 different events. There's going to be a recorder and there's going to be a speaker. So one of those could be a girl or both of them can be a girl. And I don't really care about, and I know that at least one of them has to be a girl because I only have 1 boy. So B is representing boy, G1 is girl 1, and G2 is girl 2, and G3 is the 3 girls. So I'm going to list out my table of possibilities. Okay, so then using my sample space, so the probability that I pick a girl first, so I look and I count all of the possibilities that I pick a girl first, which was 9 out of my 12 possibilities. So then I look at my probability of picking a girl second, and I count all of the possibilities in here. There are 9 out of 12. So now I find the probability of a girl first and a girl second. So I count the numbers here, and I can figure that out. So now I want to look and say, Well, 3/4 times 3/4 is not the same thing as 1/2. These events are not independent. Okay, it kind of depends on what I pick first, on what my sample is left. So it changes, the selection of the first thing, the first person, changes the things that I have left to select from. So those are not independent events. So here are some monitoring progress. Look through these and try and first think, what do you think they're going to be? Are these events dependent or independent? Then go through the math and actually solve them and figure that out. So now we're looking at some other probabilities. Now we're looking at dependent events. So this is when the occurrence does affect the occurrence of the other event. So with our girls that we were selecting earlier, if I select a girl for the first job, I only have 2 left to pick for the second position. So it does change what I'm looking at. So the probability that event B occurs given that A has occurred is called conditional probability of B given A. So there's just a different way that I write it. So I use my probability of B. This line means given A. So now let's look at some examples. First, let's look at this core concept. So we're just looking at dependent events. So if 2 events, A and B, are dependent, then the probability that both occur is the product of the probability of the first one and the conditional probability of the second one, given the first one has already happened. So let's look at that last example, right? So my probability that I pick a girl first and I pick a girl second, which is what I was looking at. So I find the probability of picking a girl first. So I count the number of times. Then I look at my sample space and I figure out, well, if I've already taken a girl first, right? So these do not count anymore because these do not go with that first probability. I have not taken a girl first. So now I'm only left with 9 possibilities, right? So now how many of those am I selecting the girl second? So that's where these come into play, right? So now I can multiply those and I end up with 1/2. So I can use this probability, the second probability that we're looking at, something has changed. So I have to change my denominator is different, right? My total sample space is different. So let's look at this example. This is example number 3. So as part of a board game, you need to spin the spinner, which is divided into equal parts. Find the probability that you get a 5 on your first spin and a number greater than 3 on your second spin. So let's go ahead and write this out. So let event A be 5 on the first spin, and B is going to be greater than 3 on the second spin. So these are independent events because my outcome of my second one doesn't depend on the first one, right? It doesn't matter what I spin the first time. I can spin anything the second time. So now I have to find the probability of each event and then multiply my probabilities together. So the probability that I'll get a 5 on the first spin, there's 1 5, so there's one good solution, right? 1 win out of 8 slices, so it'll be 1/8 because 1/8 of my pie is a 5. So now for my probability for the second part, for B, is greater than 3. So I know that can be 4, 5, 6, 7, or 8. So that's 5 slices of my pie. So the probability of B is 5/8. So now to find the overall probability, I just multiply those together, and I end up with 5/64, so approximately 0.078. So I can say that my probability that I get a 5 on my first spin and a number greater than 3 on my second spin is about 7.8%. So when events are independent, I just find the probability of each happening, and then I can multiply them together. So now here's example number 4. Let's look at this one. So a bag contains 20 $1 bills and 5 $100 bills. You randomly draw a bill from the bag, set it aside, and then randomly draw another bill from the bag. Find the probability that both A and B will occur. So if A is the first bill is $100, and B is the second bill is also $100. So first thing we want to think about is this a dependent or independent event? So I notice that I don't put the first bill back into the bag that I draw. So I know that whatever I draw second will be different because I have a different sample space. So I know that these are going to be dependent events. So I know I have to find the probability of the first one happening, and then I have to find the probability of the second one happening that A has already happened. So then I can multiply the probabilities to find my overall. So I know the probability of picking a $100 bill out is 5 out of 25. because there's 25 total bills and 5 of them are 100s. So there's my total. So that's my probability of A happening. So now let's look at the probability of B happening that A has already happened. So 4 of the remaining bills are $100, but there's only 24 remaining. So this is what I'm going to be looking at for that second probability. So now that I've come up with my two probabilities, I multiply them together, and I end up with 1 over 30, or approximately 0.033. So the chances of me drawing two $100 bills is only about 3.3%. So you'll notice in our probabilities the denominator changed, right? Because I don't have 25 bills left in the bag, I only have 24. And I've already selected, if I've already selected one of the $100 bills, there's only 4 of those left. So that's how I can determine what my second probability is going to be. So then I just multiply them together to get my final probability and my final percent. So here we're going to look at our next example. So this is going to be example number 5. So I randomly select 3 cards from a standard deck of 52 playing cards. What is the probability that all 3 cards are hearts when the first part that we're looking at, when I replace each card before selecting the next one, and then I don't replace each card, and then I have to compare those probabilities. So first thing, let's think, am I dealing with independent events or dependent events? So on part A, if I replace each card, so I start with 52 cards, I pull out one and I see if it's heart and I put it back, and then I can reshuffle, I still have 52 cards. So those events are independent of each other. Okay, so now we're finding our different events, our different probabilities. So event A is going to be my first one's a heart, event B, my second one's a heart, and C is my third one's a heart. So since I replace them, they're independent. So I have to find the probability of each one happening and then multiply them together. Well, I know that there are 13 total hearts out of my deck of 52 cards. So I know my probability of drawing a heart first is 13 out of 52. And then I put it back. I have the same probability of picking the second one being a heart, and I also have the same probability for the third one. So now I just multiply all those, and I end up with 0.16. So let's look at part B. Since I don't replace each card on this one, it depends. Since I've removed something from my sample space is different. So these are dependent events. So now I have to look at the probability of A, and then what's different the second time I pull a card, and then what's different the third time I pull a card if things are different. So I know I still have a chance of 13 out of 52 to pull a heart on my first one. Well, and since I don't replace it, I only have 51 cards left, but only 12 of them would be hearts if I've already taken out a heart. So then my third probability is, well, I've taken out 2 cards, so I only have 50 left, and I've taken out 2 hearts, so I only have 11 hearts left. Now I can multiply my probabilities, and I end up with 0.13. So now I have to compare my probabilities. So I just divide my 1 over 64 divided by my 11 over 850. So I'm 1.2 times more likely to select 3 hearts when I replace each card before the next one, right? And this is, you'll notice these numbers are actually pretty close to each other. And remember, when we're talking probability, we're always looking at numbers between 0 and 1. And so neither of these are very likely, right? Because these are both pretty close to 0. But this one is more likely to happen. So I can say that based on my probabilities. So here are a couple more that I want you to try and see how you do. First, you always want to think of, is this dependent or independent? And then from there, you know how you can find the probabilities. So here we're looking at example number 6. So a quality control inspector checks for defective parts. The table shows the result of the inspector's work. First we're looking at the probability that a defective part passes, and then B, we're going to look at the probability that a non-defective part fails. So I'm looking at the probability that it passes, but it's also defective. So I want to look at the number of defective parts passed out of the total number of defective parts. So I can find all of that information from my table. So I've got my total defective parts, which was 3, that passed. And then my total defective parts was this entire row, which is going to be 39. So then I have 3 divided by 39, or about 7.7%. So not many. So now we're going to be looking at, So now we're going to be looking at the probability of this part B here. So I'm looking at the probability that a non-defective part fails. So I want to find the ones that fail that are non-defective. So first I look at the number of non-defective parts failed, which would be right here 11, and out of the total number of non-defective parts. So I've got 11 out of my 461, or about 2.4%. So I always want to look at specifically what pieces of data am I looking at and which pieces of data am I comparing, right? Because I'm not comparing everything in this whole chart to each other. First, I'm just looking at the defective parts, and then I'm just looking at the non-defective parts. I could also be asked just about the parts that pass, or just about the parts that fail, or I could be asked about the entire thing. So it really depends on what I'm looking at here. So here's example number 7. So at a school, 60% of students buy a school lunch. Only 10% of students buy lunch and dessert. So what is the probability that a student who buys lunch also buys dessert? So now we're given some data and we have to find out some more probabilities. So event A is going to be buying lunch and B is going to be getting dessert. So I'm given that the probability of A is 0.6. So when I'm dealing with probabilities, I always want to deal with my decimal and not my percentage. So I'm always going to convert my percent to my decimal first. So probability of A was 0.6. So the probability of A and B was 0.1. So now I can find my formula to find B, that A has already happened. So I write my formula for conditional probability, right? So here's the probability that B, that A has already happened, is equal to the probability that both have happened divided by the probability that A has happened. So now I can substitute the information that I have, and I can then simplify my fraction, and I can go from there. So the probability that a student who buys lunch also buys dessert is about 16.7%. And we can also think about this numbers-wise. So if I had the group of students that bought lunch all in one room, that's kind of my sample space then, right? So I've limited to just buying lunch. And then if 10% of those students have bought dessert, then I could figure that fraction out in that proportionality. So I know it's about 16.7% of them. So now I want you to try these monitoring progress and see how you do. See if you can determine the data that we're looking at and the data that we really need. So let's revisit our learning targets. So first we have to determine whether events are independent. And we want to always determine this because then we have to know what data we're looking at and what probabilities we're looking at and how we're multiplying them together. So then once we figure out if our events are dependent or independent, now I can do the second learning target, which is finding those probabilities. So then I was able to finally find some conditional probability. So now that we've looked at these learning targets, go ahead and start working on your homework for 10.2.